Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at the trace of a matrix. So in this topic, we will define the trace of a square matrix. We will look at some consequences and consider an application thereof. Now, given that A is mapping Rn to Rn, then it is a linear operator, and A is in the space of all linear operators mapping Rn to Rn. We will define the trace of the matrix A as the sum of its diagonal entries. Consequently, like the determinant, the trace is a function mapping the space of all linear operators on Rn to the reals. Now, theorem. The trace is a linear function mapping the space of all linear operators on R to the n to the reals. Proof. Well, if A and B are linear operators on R to the n, then the diagonal entries of alpha A plus beta B are alpha times AKK plus beta times BKK for k going from 1 to n. Thus, the trace of alpha A plus beta B is just the sum of these diagonal entries. But from the properties of the sum, this is equal to alpha times the sum of the diagonal entries of the matrix A plus beta times the sum of the diagonal entries of the matrix B, which is equal to alpha times the trace of A plus beta times the trace of B. Now, previously we saw that the collection of all linear maps from Rn to Rm forms a vector space. Specifically, all linear operators mapping Rn to Rn also consequently forms a vector space. Therefore, the subset of all linear operators with zero trace is a subspace of all linear operators that map Rn to Rn. Proof. Well, if A and B map Rn to Rn and have zero trace, well, we saw in the last proof that the trace of a linear combination of these matrices is equal to that same linear combination of the trace of the matrices. But we assumed that the trace of A and B is equal to 0. So this linear combination is just equal to 0. Thus, if A and B have zero trace, then so does a linear combination of these matrices, and thus it's a subspace. Now, from calculus, you may recall that for sufficiently small epsilon, the value of a function x at t0 plus epsilon is approximately equal to the value of the function at t0 plus epsilon times the derivative, or the time derivative, at time t0. This is just a Taylor series approximation. For example, if x of t is defined as e to the negative t cos t, then the time derivative is given by this expression here. Consequently, x at some value epsilon is equal to x at 0 plus epsilon, which is x at 0 approximately equal to x at 0 plus epsilon times the time derivative at 0. Now, the time derivative at 0 is -1, while the value of x at time t equals 0 is 1. Thus, x of epsilon is approximately equal to 1 minus epsilon. Thus, this claims that x of 0.1 is approximately 0.9, which is actually quite close, as the correct answer is just closer to 0.900317. Now here's one application of the trace. Suppose we have a system that describes some real-world phenomena. In this case, we may perturb the system by adding epsilon times a perturbation or a shaking up of the system to the original model. Consequently, we'd like to know how much a small perturbation of the system may affect the results. Well, part of that is the following. The determinant of the identity plus epsilon times a matrix of the same dimension is approximately equal to 1 plus epsilon times the trace of that matrix. And this is for sufficiently small epsilon. Proof. Well, we're actually only going to show this for an upper triangular matrix U. The diagonal entries of the identity plus epsilon times an upper triangular matrix are 1 plus epsilon times the diagonal entries of the matrix U. Because U is upper triangular, so is the identity plus epsilon times U. Thus, the determinant is just equal to the product of the diagonal entries. Again, because the identity plus epsilon times U is upper triangular. Now, if we expand this out, we get 1 plus epsilon times the sum times each of the diagonal entries summed up, plus epsilon squared times lower order terms. Well, if epsilon is sufficiently small, then we can approximate this by dropping the lower order terms. So this is approximately equal to this, which is equal to 1 plus epsilon times the trace of U. For example, given this randomly generated matrix we see here, then the determinant of the identity plus 0.1 times this matrix should be approximately 1 plus 0.1 times the trace of this matrix, which equals 1.251528. In reality, the determinant of the identity plus 0.1 times this matrix is closer to 1.259198. So, of course, it's not an exact approximation, but it's actually pretty good. Following this topic, you now know the definition of the trace. You understand that it is a linear function, and you are aware of an application thereof. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!